Good afternoon, I'm Rosana Schneider. Today I will present our study on the environmental impact of microalgae production. We use the tool called the interaction matrix to do this analysis. The title of this investigation is Assessing Environmental Impact Across Different Microalgae Production Systems and Growth Media using the Environmental Interaction Matrix. Microalgae are very promising. They can be used for biofuel, fertilizer, and other high-value products. But growing them takes a lot of energy and synthetic fertilizers, which harms the environment. One solution is to use the wastewater from breweries, chemical industries, and sewage as a nutrient source. This turns waste into something useful. However, we still need a structured way to evaluate the environmental trade-offs. That is why we used the interaction matrix. The goal of this research was to evaluate the environmental impacts of microalgae production, especially Chlorella sp. We looked at the physical, biotic, and anthropic environments. We used an interaction matrix as our main tool. The matrix was filed by experts based on their real experience with Chlorella sp cultivation. For our method, we adapted the Leopoldo matrix combined with rapid impact assessment matrix criteria. We analyzed 20 microalgae production activities. We looked at 3 areas: physical, biotic, and anthropic. We consulted 5 experts in microalgae pilot production. They helped assess direct and indirect impacts. For statistical, we used the hierarchical cluster analysis and the principal component analysis, or PCA, to group the data and identify the main environmental risks. This is the method used, considering the biotical, physical, and anthropic dimensions and analyzing each stages of production. This table shows our evaluation criteria. We scored each impact based on 5 things: character, positive, neutral, or negative; importance, high, medium, or low; scope, regional, local, or punctual; duration, permanent, medium, or short; and reversibility, irreversible, partial, or reversible. Each one has a score from 1 to 3. We have evaluated different operational steps for cultivation: open ponds versus a closed photobehator, and the conventional mineral media versus alternative effluent media. For harvesting, centrifugation, chemical flocculation, bioflocculation, electroflocculation, and filtration. For drying, sun drying, oven, spray dryer, freeze dryer, and fluid-set bed dryer. We also looked at cleaning and media recycling. About results, this figure shows the negative and positive impacts of different cultivation media. We compared importance, duration, space, and reversibility across the different types of media. Here we see the impact assessment across different media. Some media had more positive impacts as brewery effluent. Some media had more positive impacts, others had more negative ones. The results helped us see which cultivation conditions are better for the environment. For biomass separation, centrifugation, and chemical flocculation have high energy use and produce chemical sludge. Bioflocculation and electroflocculation are greener alternatives. For drying, spray drying, and freeze drying need a lot of energy, so they have negative scores. Some drying cuts emissions, but raises the risks of contamination. In the dendrogram A, from matrix data, the formation of three main groups can be observed. The first group is associated with economic and social aspects and the quality of the final products, characterizing them as positive impact. The second group lists impactful activities from potentially adverse effects on water, soil, atmosphere, flora, and fauna. The third group is related to negatively impact environments, being more frequent in all stages of microalgae production. Figure B shows the PCA score chart using data centered on the average obtained from the matrix that covers all stages and actions analyzed. The most positive impacts were grouped on the positive side of PC1, while the negative impacts were grouped on the negative side of PC1. The negative impacts are associated with spillage and disposal of the cultivation media in the soil or water, covering the majority of actions evaluated. Indeed, the intensity of impacts related to costs, use of natural resources, and use of water stands out on the negative side, highlighting the significance of these negative impacts. We identify four main risks. First, wastewater spills can contaminate the soil and water. Second, biomass growth in wastewater cannot be used for food or medicine, only for biofuels or fertilizers. Third, centrifugation and thermal drying cause over 60% of negative impacts. Fourth, recycling the culture medias after separation greatly improves water and nutrient efficiency. For sustainable production, we recommend three things. First, use low energy harvesting, like bioflocculation with solar or fluid bed drying. Second, recycle the growth media to reduce water use. Third, implement containment protocols for effluent feed ponds. For strategy, use wastewater biomass only for bioenergy or biofertilizer, and use the iterations matrix early in industrial scaling to find the environmental hotspots. We found two main groups: the anthropic effects com more positive social and economic points, and the biotic effects with more negative environmental impacts. Using effluents for microalgae has potential, but also risks like spills and contamination. We need a careful decision making, choosing technologies with lower risks and higher biomass production. Expert guidance is essential for a sustainable and balanced approach. Thank you.